Hi, my name is Alex Jasper, and I am majoring in software engineering. For my honors project, I designed, manufactured, and programmed a robotic quarterback to compete at Notre Dame's robotic football event. I hope you enjoy the following presentation.
Robotic Football by Alex Jasper. To start, I would like to give a little more information about how the history of robotic football began. In 1995, Notre Dame student Brian Hederman passed away in a car accident. Brian's dad, who wanted a better memorial for his son, had found drawings in his room of robotic football players. Thinking this was the perfect memorial, Brian's dad then reached out to Notre Dame, who started a robotic football senior design project in the early 2000s. Eventually, the project expanded into a full robotic competition that is now held every year, consisting of various surrounding engineering schools. Some of these schools include Purdue, Ohio Northern, and Valparaiso. Similar to the NFL, there is a combine where robots participate in different drills like speed, agility, push tests, etc. In addition, there is also a round-robin tournament to conclude the event. Next, I'd like to discuss how the project began. The concept started in the spring of 2019 in Logic and Computer Design when Dr. Sharma proposed robotic football as a lab project. He handed out a flyer describing the event, and after reading the description, I immediately wanted to participate since I had been a member of my high school's robotics team. By the end of the semester, a partner and I developed a quarterback prototype out of plywood and 2x4s, which you can see here. We presented our robot alongside the Senior Design Expo and had immense interest. We even played catch with Expo visitors. However, this design did not meet all of the restrictions of Notre Dame's event, hence the start of my honors project. Since the previous design didn't meet all of the restrictions, I first needed to refresh myself on all of the rules and regulations of the event in order to make sure the robot would be compliant. Here are the requirements for a quarterback. Starting with the chassis, it must be made with a minimum of half-inch HDPE or high-density polyethylene. HDPE is similar to the material of a plastic cutting board. The base or bottom of the chassis must be 3 inches off the ground with a 0.2-inch tolerance. In addition, the perimeter of the robot must have a rubber bumper strip mounted at a maximum of every 3¼ inches. Finally, the dimensions are restricted to a 16-inch square by 24 inches tall and must not be more than 45 pounds. Additionally, at least one high-intensity LED must be visible from all directions. This LED is connected to a tackle sensor developed by Notre Dame. The tackle sensor determines if another robot has driven into you. A change in LED color means that you have been tackled. I will demonstrate this later on. Finally, all robots must have an ID number and a kill switch in case of malfunction. After refreshing myself on the requirements, I set to work designing the robot. Thanks to help of a few colleagues, I was able to learn the basics of CAD and created the design in SolidWorks. The design mimicked much of the previous design, but adjusted for dimension restrictions. Additionally, walls and a top were added to protect the electronics. After speaking with some engineers at Burr Oak Tool in Sturgis, Michigan, they provided some feedback on the design and offered ideas for improvement. One suggestion was to use helicoil inserts to hold the chassis together instead of using the dovetail design, which you can see here. Helicoils are a threaded metal piece that bolts can screw into. They allow for easy assembly and disassembly, as well as part reuse. Taking that feedback into consideration, I altered the design in SolidWorks. Upon completing the design, Burr Oak graciously offered to manufacture the chassis with the HDPE we provided. Taking my three-dimensional CAD models, I converted them into two-dimensional drawings, labeled with all of the dimensions for holes, hole diameters, and other cutouts. The two-dimensional drawings are what Burr Oak uses to program their machines for the manufacturing of parts. This drawing that you can see here is for the base of the chassis, which was the most complicated by far, as 50 holes were needed of all various sizes. Additionally, the design is easily transferable to other types of robots. Other Trine students that are developing different robots are using my same drawings for manufacturing. Next came the electronics and wiring. Referencing the prototype, I rebuilt the circuit, soldered connections on the motors and actuators, and added a protective heat shrink over exposed areas. In addition, I spoke with members of the Notre Dame team to learn how the tackle sensor functions, as well as how to wire the LED to it correctly. Afterwards, the electronics were mounted inside the chassis. Here you can see the inside of the robot with all the electronics and wiring complete. Since I had already developed a working prototype, the software was reused for this robot, as almost all of the functionality was the same. Previously, my partner had written the driving portion of the software, and I wasn't satisfied with how it turned out. I redesigned the driving software to my preference, which functions similar to that of a zero-turn lawnmower. The robot is operated wirelessly using an Xbox 360 controller, which you can see pictured here. An Arduino microcontroller, the red square pictured, processes the Xbox input and broadcasts a signal over radio frequency. That signal, or command, is received by another Arduino inside the robot, which decodes it to control the robot's functionality. The radio frequency transmission is over the 2.4 GHz frequency and is compliant with the IEEE 802.15.4 standards. The radio frequency communication is handled by XB modules, which broadcast and receive commands. Next, I have various clips of the robot in action. These videos include driving, throwing and throwing accuracy, tackle sensing capabilities, and the ability to receive a hike. Enjoy! I would like to thank Dr. Sharma for providing a means of making this project possible, from equipment and materials to guidance and continued help throughout the entire process. I also want to thank Mr. Marvin Herman at Burr Oak Tool for not only providing industry feedback on the design, but for manufacturing all HDPE parts that went into the project. Finally, I want to thank my colleagues. Thank you, Dylan, for developing the original prototype with me and for putting us in contact with Burr Oak. Thank you, Isaac and Levi, for teaching me how to use SOLIDWORKS and your guidance with the CAD designs.
Unfortunately, due to the current health concerns, I was unable to compete this year as the event was canceled. I hope you enjoyed learning about my honors project. Thank you for watching.